8.5, we're using exponential and logarithmic functions for growth and decay. And so we're going to start with the continuous exponential growth. Okay, so you can have this as f of x equals or y equals. We're going to use those interchangeably. So it's f of x equals ae to the power of t. Okay, and this is where a is your initial value. T is going to be the time. And then we call K the growth rate constant. So depending on the situation, there will be a constant that represents the growth rate for that particular situation. Okay, and the continuous exponential growth equation, like I said, sometimes it's y equals the value. That is often used to represent population growth. And it really is the same as the compound interest formula, the PERT, except instead of P as your initial, it's A as the initial. Okay, and then your output is your amount at that time. And then R is the interest rate in PERT, and K is the interest rate in continuous exponential growth. Okay, so this is another way to write your equation. Okay, and then just as a reminder, in Chapter 8, all of your story problems need to be solved algebraically. So that means you're going to solve it with logs. If you're solving algebraically, that means you are not solving graphically. So in earlier chapters, I showed you how to solve using the intersection feature on your graph. We already assessed that. For this chapter, we are assessing if you can use algebra and your logs to solve. So what we're going to use today to solve is the natural log. Okay, so whenever you have the value of e, you're going to be using the natural log to solve. And remember, the natural log is ln. Okay, so we're going to be using ln to solve today. Okay, so example 1 says the initial population of rabbits in an area is 8,000, and the population grows continuously at a rate of 26% per year. Okay, so the initial population is 8,000. It grows continuously at a rate of 26% each year. What we have to do is write an equation to represent the rabbit population, okay, which they're calling P, and it's measured in thousands after T years. So if they're giving you these variables, these need to be in your model, in your equation. Okay, but notice here that P is in thousands. So when they give you the initial value is 8,000, if it's measured in thousands, you don't want to plug in just the 8,000. You want to divide it by that unit. Okay, so the function is built for thousands, so your value of A is going to be 8. Okay, so if it's measured in thousands, you're going to divide by 1,000 to find what that value is. Okay, and then we are used to writing the percent as a decimal for the rate as your 0.26. When you are dealing with your continuous growth equation, that constant is K. So R is 0.26. That's the same thing as saying your value of K is 0.26. Okay, so that's what we're going to plug into our equation. Whenever you are writing an equation, you need the values of A and K. also need your output and you need your input. Okay, so that tells you that your output is P, so we're going to use P equals. Sometimes they might say Y. Okay, and then our A value is 8. And then it's E to the power of KT. Okay, now they already tell you that T is measured in years. Okay, so you don't have to specify that, it's already specified. So your equation is P equals 8E to the power of 0.26T. Right, and then for example 2, it says an experiment starts with 20 bacteria A cells. After 45 minutes, there are 710 bacteria A cells. For part A, we are going to write the equation that models the number of bacteria A cells, Y, after T minutes. So you're writing an equation, Y, after T minutes. Okay, so when you're writing an equation, you are writing an equation of this form. Just like we did in example 1, you are going to have to find the values of A to plug in and the value of K. So let's organize what we're given. So the variables that we know. So based on what we highlighted, it starts with 20 bacteria A cells, so that would be our value of A. And then this says after 45 minutes, there are 710. So this means when T is equal to 45, your Y value is 710. So if we need to find A and K, just like we did here, we already have our value for A. We are going to have to solve to find K, and that's where this comes in. We're going to use this to find K. Okay, so the output is 710 when your initial value is 20. We don't know K, we have to find that, and your time is 45. Okay, and we can solve this for the variable K. The first step is to isolate E. So to isolate E, we're going to divide both sides by 20. And then if you remember from last week, if you can simplify this, you will. Like I know if I divide them by 10, those cancel out. And that just helps me work with some smaller numbers there. K times 45 is the same thing as 45K, so I'm going to write it like that. And then once you get E by itself, that's when you can take the natural log of both sides. Okay, you do have to show that step that you're taking your natural log. And then from there, those will cancel. You'll get 45K. Okay, and then we're going to divide both sides by 45. So I'm going to divide this by 45. It's okay if you don't want to rewrite that part again and you just write it here. That's your value. And then we're going to round this to 4 significant figures. Have you guys talked about significant figures in some of your science classes? Okay, so if we do the natural log of 71 divided by 2, make sure that we close that. And again, you can leave that as 710 divided by 20, that's fine. I just do that because that's easy to simplify in their heads and then I don't have to write it down as much. Okay, so if it's 4 significant figures and we have that starts with 0.0, that means you want 4 values after that. So it would be 7932 would be rounded. Okay, so this one is 5 decimal places. If you want, you can always do the 5 decimal places. That's a safe bet to do 5 decimal places. Okay, so you can use that rule when you're solving for K. 5 decimal places or 4 significant figures. All right, and so from there we can do our model. So remember, model and equation, those are interchangeable. So we have y equals, our a value is 20, and then it's e to the power of 0.07932, and then don't forget the value of t. And again, they tell you it's after t minutes, so if they already put in there what t is, you don't have to identify that. All right, now for part B, it says after how many minutes will there be 1,000 bacteria A cells? Okay, after how many minutes will there be 1,000 bacteria A cells? Okay, so if they're asking you how many minutes, that means you're trying to find the value of t. Okay, so you're trying to find t when your y value, okay, when the output value is 1,000. Okay, so if I plug in 1,000 for y, I have 1,000 equals 20e to the 0.07932t. So our first step is always to isolate the e. So if there's a number multiplied in front, we're just going to divide. Okay, and then when you're dividing, you can always divide by 10 first, and then you have 100 divided by 2. What's that? 50. Okay, you can also use your calculator to do that. If it simplifies, that's fine. And then I always like to leave a little space here because when you are doing the natural log, you want to put that right in front. Okay, so then the natural log and e cancel out because they make 1, which gives you 0.07932t. And then I know that some of these decimals are long, so you just want to put the quotes underneath it, and then on this side put what you're actually dividing. I'm fine with that. I just want to be able to see like how you're getting to your value of t, which is going to be this part here. Okay, that division. Okay, so let's go ahead and divide that. It doesn't say what to round to for part B, so if it doesn't say, you can decide. I would either round to the nearest tenth or 100th. For this one, I'm going to round to the nearest 100th. So I have the natural log of 50 divided by 0.07932, which is going to get me approximately 49.32. And in time, you want your units. So this is in minutes, because it tells you here how many minutes. Okay, and then for part C, it says bacteria B, so a new type of bacteria, grows exponentially according to, and then this would be given to you. So there's a model for bacteria B that's y equals 52 e to the power of 0.064t. So 52e to the power of 0.064t. Okay, after how many minutes will there be more bacteria A cells than bacteria B cells? And it does tell you to round to the nearest 10. So after how many minutes, so that means time, will there be more bacteria A than bacteria B cells? And we're going to round to the nearest 10. Okay, so what we're trying to find here is we're trying to find T because we're finding the time. Okay, we want to find T when bacteria A, the amount of bacteria A, is greater than bacteria B. So we're going to set up an inequality here. We have to find the time when the bacteria, bacteria A is greater than bacteria B. Okay, so the model for bacteria A is 20 e to the 0.07932 t. So we're going to set that up greater than our model for B. Okay, so we have an inequality here with models on both sides. Okay, we haven't solved anything where you have the e's on both sides. Normally what we would do is, if we were trying to solve this, is we move over 20, right? But if we move that over, we're still going to have something in front. So instead, when you have models on both sides, we are going to use our product property rule. Okay, so that's going to start by taking the natural log of both sides. So we're going to take the natural log of 20e to the 0.07932 t. We're also going to take the natural log of the other side. And then we're going to rewrite using the product rule. The product property. So remember the product property tells us if you are multiplying two of these together, then you can separate this into the natural log of 20 plus the natural log of e to the power of 0.07932 t. And then see if you can write what the other side would be based on this. So you should have the natural log of 52 plus the natural log of e to the 0.064 t. So what does that allow us to do next? What do you guys think our next step should be? Yep, we're going to cancel out the natural log and the e, and we can do that on both sides. So we have the natural log of 20 plus 0.07932 t. That would be greater than the natural log of 52 plus 0.064 t. And then keep in mind you are solving for t. Okay, so it's just like if you had x's on both sides, you would want to get them all on one side. It doesn't matter what side you want to get them to. I generally try to keep them positive. So I'm going to move the 0.064 t over. So I have 0.07932 minus 0.064. That is going to give me 0.01532 t. And when we move all of the variables to one side, what that means is we want to move all of the numbers to the other side. So this natural log of 20, I'm going to move to the natural log of 52. So I have the natural log of 52 minus the natural log of 20. And you can leave it like this. If you do, before you divide, you do want to make sure you have those in parentheses, or some of you might realize that that's the quotient rule, because if you have minus, you can write it as the natural log of 52 divided by 20. You can write that as either way. And then your last step is going to be to divide by 0.01532. Okay, so when I say you have to do that first, I mean you either need to do the natural log of 50 minus the natural log of 20 and press enter, then divide by 0.01532. Or you can do the natural log of 52 divided by 20 like that, and then divide by 0.01532. Okay, if you put this all in at one time, you just have to make sure you put your parentheses on there. Okay, so if this one says to round to the nearest tenth, so it'll be 62.4, and this will be minutes. Okay, so this means when the time is greater than 62.4 minutes, that is when bacteria A is going to have more bacteria than bacteria B. Okay, so everything we talked about on the front side was about growth. Okay, and if there is growth on the opposite side, there is what? Decay. So I mentioned to you guys that there are some scientific applications of the exponential decay. Your equation is almost identical to the growth. It can be f of x equals or y equals. I like the y equals better. Just because if it's, I don't like the f of x if you have t as your input. Okay, so it's f of x equals or it's just your y equals. Okay, but the difference is you have that negative value for k here. Okay, so just like before, your value of a is your initial value. T is your time. And now the K is called the decay constant. Before it was the growth rate constant, and this one is called the decay constant. Okay, and then it's helpful to think of your Y as your amount remaining. So if A is what you start with, Y is the amount that you end with. Okay, and one of our applications has to do with the half-life of a substance. So many substances have a half-life value, and it is what it sounds like. Half of the life is how long it takes for it to be half remaining. Okay, so the half-life is the time it takes for a substance to be cut in half. Okay, it's the time it takes for a substance to be cut in half. Okay, so if the half-life is 10 days, that means whatever you start with in 10 days will be half of it remaining. Okay, and in our example 3, we're talking about the element chromium-51. That has a half-life of about 28 days. So we have to, for part A, determine the value of K, so determine the decay constant, and the equation of decay for chromium-51. Okay, so what we know is the time. They give you the half-life of 28 days. So the time is going to be 28 days. We have to find the value of K, but there's no initial value given. If you are not given an initial value, you can choose what you want it to be. So if no initial value is given, you can choose that value. Okay, so generally what I choose if they do not give that to me is I choose 1, and B, you can see it's like it says 650 milligrams, so I'll usually choose like the 1 milligram. The unit doesn't necessarily matter for this first part. Okay, so if my initial value is 1 milligram, then after 28 days, how much is remaining? Yeah, so after 28 days, the Y value would be half of a milligram, right? Okay, so when we set this up in our equation, again, we're using this, just the Y equals AE to the power of KT. The remaining amount is half when you start with 1, and then it's E to the negative K. Now, I said that you could start with anything, right? Somebody give me a number. You guys have a favorite number? 100. Okay, so if you start with 100, okay, in the same equation, you don't have to write this down. We're just going to look at it. Okay, if you start with 100, no matter what these values are here, how much would you have remaining after 28 days? 50. Okay, so if you did that, your first step to solve would be to do what on both sides? Divide by 100. And on 50 divided by 100 is what? 1/2. And then look, do you see how what you have here is exactly what we have already? So that's why I choose 1, just because I feel like it saves me a step. Because you can really pick anything, but you know 1 times anything is itself, right? So then you can just go into your natural log. You can do the natural log on both sides here. 1 times anything is itself, so that doesn't make a difference. These are still going to cancel out, and we have negative 28 times K. I write it like that because I like to multiply it. You don't necessarily have to write it the exact same way. Okay, and then we're going to divide both sides by negative 28. Okay, and again, we'll just do that to 4 significant figures or 5 decimal places. So that 5 is going to get bumped up by the other 5. So 0.02476. And it says that we had to determine the value of K, so we did that. This is our decay constant. And just again, the reason why this is allowed is because 1 times this is the same thing. So you could write it in another step without the 1 there. Do you guys remember what the natural log of 1 is? So if you were to use your, sorry, I did type it here. If you were to do your natural log of 1 with your power rule, it would just be 0 plus, like what we did in the last one. Okay, so it's okay to cancel those out. Now we're going to write the equation of decay. But remember, they did not give you an initial value. So if they don't give you an initial value, you are just going to leave it as A in the function. So this is y equals AE to the power of negative 0.02476 t. Okay, and you are doing the equation of decay. It doesn't say what T is, so you're just going to say what it represents here, and it's based on the half-life. So in this case, it's where T is the time in days. In our other examples, they told you where T is the time in whatever unit. And this one, it didn't say, so we're going to identify that. Okay, and again, there was no A value given, so if there's no A value, you're going to leave it just like this when they ask you for your function. All right, and then for part B, it says how much of a 650 milligram sample will be left after 30 days. So how much of a 650 milligram sample will be left after 30 days? So when they're asking you how much is going to be left, that means you're going to be finding your value of Y. So what they do tell you is it starts with 650 milligrams. So that is your initial value for this. Your time is going to be the 30 days. And you can just plug this into your model. So Y equals 650 E to the power of negative 0.02476 times 30. And again, it doesn't tell you what to round to, so you can round to the nearest 100th or 10th. So when you're finding Y, you are just going to evaluate. Don't forget your negative for the decay. Okay, so it's going to be 309.26 milligrams, or 0.3 if you round to the nearest 10th. All right, and then let's take a look at what part C is asking. So how long will it take for the 650 milligram sample to decay to 200? Okay, anytime they're asking you how long, that indicates you're going to find T. Okay, and it says how long will it take 650 milligrams, so that's what you start with, to decay to 200. So that's going to be your Y or your output. So we got 200 equals 650 to the power of 0.02476. Okay, and then I want you guys to see if you can solve that for T. So we've done that a few times today. And then, like I said, when I'm reducing this, I just do it quickly. I could reduce that more. You don't have to. I just reduce it by the zero so that when I'm writing this out, I'm not writing as much out. And then the natural log and E will cancel. Okay, and then I'm fine if you want to do the division at this step. Okay, the main thing I want to see is what you're dividing to get to that value of T. Okay? And does this tell you what to round to for part C? The nearest 10. Good. don't even have to reduce that at all. Again, the reason why I do that is so that I don't have to write out as much. Okay, so this is going to be 47.6 days. That is going to be your value for T. Okay, and then our last example is also about the half-life. We have a radioactive substance, and it has a half-life of 24,110 years. Well, a lot more than those 28 days. So the radioactive substances do take a long time to decompose. Okay, and they tell you that the decay constant is 0.0000287. So in some of our earlier examples, we had to find K. This one, they're giving it to us. So in part A, they're asking how long will it take. So how long will it take to have 75% of the sample remaining? So 75% remains. Okay, and there's a couple different ways you can set this up. I'm going to show you two different ways with our different steps here. So one way you can think of this is if they don't give you an original value, you can just think of your original sample as A, because that's the variable we use. And if 75% is left, the 75% of the original A, do you guys know how we could write that? Yeah, it's just 0.75A. So you could write it in terms of the variables. And then what you're trying to do is you're trying to find T. And so we can plug these values into our y equals AE to the negative KT. So our remaining value would be the 0.75A, that would go in for Y. Our original value would be A. They give us our value of K, so if K is positive, when you plug it in, that minus is still going to be right there. We have 0.0000287 T. Okay, and then if we're trying to solve that for T, our first step is always to move over what's in front. So we would divide by A, which of course is going to cancel out here, but it's also going to cancel out on this side. And then once you isolate the E, you can take the natural log. That's going to bring this down in front. And then we know to get T by itself, we're going to divide. So again, if you want to use those quotes there, I know that's a bigger decimal. Again, this is what we want to see, like how you're getting that value of T. Okay, and then this is to round to the nearest year. So anytime you're rounding to the nearest year, that means you're going to round to the nearest whole number, and you're going to use your normal rounding rules. Okay, so we have the natural log of 0.75 divided by negative 0.000287. Okay, so if I'm rounding to the nearest year, I'm just going to look at that decimal right after. Okay, so that 0.7 is going to bump that up to 10,024. And this is in terms of years. All right, now let's look at the language in part B. It says find how long it takes to lose 75%. So here it was have, this is lose. So if you lose 75%, how much is remaining? 25. So when you're setting up your equation, losing 75% means you have 25% remaining. Okay, so another way you can do this, I showed you in the first one is, think of your original sample as A and then do 75% there. Okay, you can also think of your original sample as 1 like we did before, and you can write the 25% remaining as 0.25. Because just like we had with the variable here, we divided by A, those are going to cancel out. So you can think of this as, I only have 1. Okay, so if you think of the original as 1 and you have 0.25, or you can even write it as a 4th, that's fine too. Okay, then we can do what we did in part A in our last example, where you can start by taking the natural log of both sides. We know that 1 times anything is itself, so this natural log is going to cancel out with your E. Okay, when you have those longer decimals, I'm fine if you use the division there, and I'm fine if you just leave this and write what you have here. Again, we want to see this. Okay, what you're dividing by to get there. Okay, this is another one that says to round to the nearest year. So round to the nearest whole number. And look, if you have a calculator like this, you can even just enter this. You can go back and change this to 0.25. Okay, so you get 48, 302, 0.9, dot. So this would be 48,303 years. Okay, that's a long time. Okay, and then 8.5, this is the last section in chapter 8. Okay, and that is your homework that is due tomorrow.